Hello, Garrett of Trackless Blue Studios here. In this devlog, we're going to talk about how I fixed the level generation in my first commercial game, So I Mine. Before we get started, let's talk about how the levels work in my game. Levels are a fixed length, they have a common ending section, they should avoid overlaps, they should avoid no-go areas. We don't want to spawn the level in full, we create data up front and instantiate during gameplay. They must reach a certain height before placing the common end section, and they are primarily made up of tunnel sections that I internally call pipes. What is a pipe? A pipe is a pre-made tunnel piece. It contains an end transform to attach the next pipe to. It also contains a spline that determines where rocks and other objects are spawned. Let's get started with my first iteration that I call random, but with some rules, or RBWSR for short, because we are software engineers and we must acronym everything. First, a straight pipe is part of the static level, so it's the first enum value we pick. Then we create two counters, D to handle pipe directions, and U to handle forcing an upwards pipe. It's also worth remembering that this version uses pure enums. There's no concept of world space, and the placement I'm doing in the example is just for illustration only. Let's do a walkthrough of the first algorithm. For X pipes, where X is the length of the level, randomly choose a pipe enum. In this case, we've chosen a straight pipe, so if D is equal to 2, then we can't choose a right turn, which doesn't apply. If we chose a right turn, we increment D, which also doesn't apply. If an up pipe isn't chosen, we increment U. That does apply for this iteration, so we increment U by 1. If U is equal to 5, we force an up pipe and reset both U and D, which isn't the case here. We then add this selected pipe enum to our array. For our next iteration, we also choose a straight pipe, which results in the up counter being increased by 1, and we add it to our pipe enum array. The third pipe we choose is a corner piece, so we have to increment our D counter by 1. We then head straight again, and we choose a corner piece. Our D counter is now equal to 2, which means we can't choose another right turn piece until the counter is reset. At this point, our U counter is now 5, which means we have to force an upward pipe, which resets both U and D. This means on our next iteration, we're able to choose a corner pipe, increment D by 1, and add it to our collection. We then finish the level by adding 3 more straight pipes. Well, let's start with the good. It's super simple, and it is somewhat effective. It's really quick to make, and it is good enough for a demo if you can find a seed that doesn't break easily. And the bad? Some seeds will be prone to errors, it's possible to enter no-go areas, it's possible for pieces to overlap, and finally the generator has no idea where a pipe is in world space, it's purely enums. Before I could get started writing a better level generator, I wanted to make pipes more data-driven. That's so we could add things like a spawn chance or a spawn cap, and we could also bake other data alongside that, like the pipe's length and the connecting end transform. This also means that levels can contain different pipe sets, and more importantly, the level generator can understand where in world space it's placing pipes before we actually instantiate them. Here's the second iteration, a 3D tile grid, or 3D TG. Create a grid of 3D cells that fill the entire play area. Introduce current last transform variables so the generator knows where we are in the world. No need for the direction counter, as it should be handled by tile claims now. However, we do keep the up counter, as it's crude, but quite effective. Here's a quick run through of the tile grid implementation. For X pipes, we get potential pipe data based on the spawn chance spawn cap. In this case, we've chosen the straight pipe. We then calculate the world space position of the pipe using the current transform. We then check if the pipe can be placed in the grid cells using the baked tile data. If no pipes are valid, then we perform a rollback, which we don't need to do in this case. We claim the grid cells and then combine the current transform and the end transform of the selected pipe to determine the new current transform. And finally, we add this pipe data to our final array for the game to use. In this example, we repeat this for several pipes until we hit a scenario where if we place another pipe, will cause an overlap. So we need to perform a rollback. A rollback is when we detect a bad pipe placement and we need to roll back to the previous iteration of our loop. We also add the pipe we previously placed to an ignore list using a transform pipe key value pair. This means, in theory, we won't repeat the same mistake twice. For the super smart, there's a bug in this ignore list setup. However, I'm not super smart, so this wasn't fixed until iteration 3. We roll back to our last transform, which I'll mark as T1, which puts us at the end of the last piece we placed, which is this corner pipe here. As we can no longer place a straight pipe at T1, we choose an upwards piece and place 2 further straight pipes to complete the level. Our actual output of the algorithm is now a collection of pipe data resources. The good? It's useful for tiled levels. Grid cells can be claimed by a pipe, we can visually debug it, and we can mark tiles as claimed for no-go areas. And the bad? My pipe pieces weren't made with tiles in mind. I had to add tooling scripts to bake tile data so we knew which cells to claim during generation. It ended up being a little bit slower than expected. It felt very rigid and more complicated than it needed to be. I had to try multiple approaches at baking data that would work with the grid, and still ran into random bugs where the middle parts of the pipe wouldn't be detected, which would cause overlaps in the generation. And here we are at the final iteration that I call Just Use Physics. Made use of Godot's existing function to bake convex collision mesh points into pipe data. Introduce a transform stack to track where each iteration of our generation loop is in the world space. Our final example, it's very similar to iteration 2, but rather than claiming tile grid cells, we effectively claim an area in world space using convex bodies. For X pipes, get potential pipe data based on the spawn chance spawn cap, calculate world position of the pipe based on the current transform, and check if it can be placed in the world. Placement checks create a convex collision area/body and check for overlaps using a specific collision layer. If no pipes are valid, then we need to perform a rollback. If successful, keep the generated convex body, combine current transform and the new pipe's end transform, and add to the transform stack for next iteration. And finally, add the selected pipe data to our array. Our transform stack is shown here by the numbered green dots, so we're able to track the world position of every iteration of our algorithm. At iteration 7, we've run into a scenario where the straight pipe piece that we've placed overlaps with the entrance no-go area, so we need to perform a rollback. For iteration 3, I updated the rollback procedure. When we detect a bad pipe placement, we roll back to the previous iteration of our loop. Any physics areas or bodies need to be cleaned up. We add the pipe that we previously placed to an ignore list using a transform pipe key value pair, and in theory it did mean we wouldn't make the same mistake twice. And in part that is true, it would be way more than twice. In fact, you could get stuck in an infinite loop. An explanation of the rollback bug: a transform key T1 with a singular pipe value breaks very quickly. Let's say we roll back once. We can no longer place a corner pipe at transform T1. We now place a straight pipe, we need to roll back again. We can no longer place a straight pipe at transform T1. We've just overwritten ignoring a corner pipe at T1. It's now possible to repeat this indefinitely until hitting the failsafe. Luckily, the fix is simple. Just use an array of pipes as the ignore value. This is somewhat of a worst case scenario for our rollback system, where at transform 7, we aren't able to place any pipes available to us. So we need to roll back again to transform 6, where we're able to place a straight pipe and complete the level. The good. A bit more work to set up, but it solves all the problems of the first and second versions. We can make use of Godot's physics server directly for super fast processing. It provides us a more organic use of world space. Convex collisions can be inaccurate, but are probably good enough for my use case. I was able to reuse a lot of concepts from iteration 2, like the rollback, pipe data, tooling, baking, and the tracking transforms. Creating no-go areas is now trivial. We simply use Godot's area nodes and place them in a level. Creating temporary areas and bodies is easy to manage using physics server and RIDs. A RID is a resource identifier. It's basically Godot's way of giving you a handle to an object. And the bad. It's slightly less easy to understand. There's potential for some of the physics checks to be slow on some machines. Could create more bodies than Jolt could handle. Jolt is the default physics engine that Godot uses. Now this isn't too likely, but it's still a concern. It doesn't create any nodes, so debugging could be difficult. It ended up working almost instantly though, so I didn't really need to debug. What could go wrong? And nothing has gone wrong so far. If you've made it all the way through the video, thanks so much for watching. And for no other reason than I can, here's a giant level that I generated using the final algorithm. Enjoy. Now that probably shouldn't be there. It's probably a bug. Oh ho, a delightfully devilish ruse. It's just the announcement to say that Demo 2 is now live on Steam and itch.io. It includes a new player leveling and XP system. Gaining levels will provide you with random perks. It also includes the rewrite of the level generation system and much more. So give it a try. Thanks again for being here. I'll hopefully see you in the next devlog. I have no idea what it's going to be about yet, but I'm sure I'll throw something together. See you soon.